So my name is Jintai, so I will give a lecture on multivariate public key cryptography. So I will skip what I said earlier, then let's just go to the lecture directly. The lecture contains 5 parts. I do a brief introduction. I will tell you a little bit about the 2 signature schemes and then the encryption screen. And in the end, I will talk a little about security analysis. Okay, so this is the main structure of the talk. So let me start with the definition of multivariate public key crypto. What is multivariate public key crypto system? It's a crypto system whose public key is a set of multivariate polynomials. So the public key are given as a set of multivariate polynomials over a finite field. Okay? And in the mathematical term, that means we have a public key which consists of G1 to Gm. And each of them is a polynomial in n variables, x1 to xn. This is a polynomial over a finite field. Yeah, so this is a public key. And the plaintext are given in the form of a vector over the finite fields. Let's call it m, which is x1 prime to xm prime. Okay, so this is your plaintext. And to encrypt is very simple. The encryption means you compute the value of the polynomial. Yeah, so you compute the value, then you plug in those x1 prime to xm prime, you compute the value, you get a y1 prime to ym prime, and this is your ciphertext. Okay, to decrypt, the things are very different. There are many different designs. Of course, we know decryption process is an inverse process of encryption process. Therefore, essentially, you have to compute the inverse of map G. So I wrote G inverse here, but this inverse is slightly different from mathematical definition of inverse because this map is not necessarily bijective. But so here, the G inverse means find the pre-image. Okay, so that's the basic design. Yeah. So I'll just give you a small, simple example. For example, let me start a finite field, which is GF2, degree 2 extension with GF2. So this is GF2 modulo x squared plus x plus 1. So there are 4 elements. Just to simplify notation, I use 0, 1, 2, 3 to represent the elements, and they have additions, multiplications, and so on. So suppose my public key is G0 to G2. So these are 3 polynomials, each with 3 variables. So this is the quadratic polynomials. And suppose you have a plaintext, which is x0 equal to 1, x1 equal to 2, x2 equals 3. So what do? You just plug in the values into the polynomial, and you compute the value. In this case, you will get a y0 equal to 0, y1 equal to 0, and a y2 equal to 1. So that's it. That's the encryption process. It's very simple. Yeah, given polynomial, you compute the value. That is done. Okay? And this map actually coming from what is called a Massimo image system, which I'll briefly explain later. And this is actually a bijective map. Okay, so this is why we could do decryption. Therefore, we can do inverse the map. Therefore, do the decryption. So let's look at the signature scheme. Signature scheme essentially is the same, but the roles playing change slightly. So suppose you have a document, and its hash value is given y1 prime to ym prime. Okay, sorry, there should be m here. There's a typo here. Okay, it should be y1 prime to ym prime. So if you want to sign the documents, what you have to do is actually find the inverse of the map, which means you apply G inverse to y1 prime to ym prime, you get x1 prime to xm prime. So that's it. So therefore here, your signature is given by x1 prime to xm prime, and your hash value is y1 prime to ym prime. So how do you verify if the signature is valid or not? It's very simple. You have these 2 pairs, and you plug into your public key, which means you compute the value gx1 prime to xm prime. If the value indeed equal to y1 prime to ym prime, you accept. Otherwise, it's an invalid signature. So that's the basic idea. Okay? Yeah, so this is it. Yeah, and how about the security? And if you look at what we have done, you can easily see that if I have the ciphertext, which is ym prime to ym prime, if I know the public key, it is very clear that the plaintext is one of the solutions, if it's not a unique solution. So therefore, if you can solve the system, you defeat the scheme. So the security relies on how hard it is to solve a set of polynomials. Of course, we have a known proven result. It is that to solve a random selected nonlinear polynomials over finite fields is NP complete. So it's a very hard problem. This is what we know. Okay, so the security relies on that. Of course, it does not guarantee everything is secure if it's not properly designed. So this is where the fundamental idea comes from. Okay, so this is a security. And then let's look a little bit about solving polynomial equation. You would ask hard. Yes? So let's look at human history. I think this is very interesting. Yeah. So what can we humans do? So about 3,000, 4,000 years ago, we could solve quadratic equation with 1 variable. This is done by Babylonians. So 1 variable, degree 2, we could do 3,500, 3,600 years ago. Okay? And then how about 1 variable, degree 3? Okay, how long does it take? So about 3,000 years. So we jump from degree 2, single variable, to degree 3, and this is Tartaglia and Cardona. Of course, there's a big dispute here, so I don't want to tell you the story. But anyway, so it took us 3,000 years, more or less, to go from degree 2 to degree 3. Okay? How about the multivariate case? The multivariate case, of course, this is the proposed solution is done by Bookerberg in 1964 to 65. He invented what is called a global basis. Okay? But actually, I think Hironaka also in Harvard had a similar ideas, and nevertheless, he called it standard basis. So if you look at mathematics, these two things are essentially the same. But Hironaka clearly is not interested in computation, therefore, he didn't do much afterwards. Anyway, the basic idea came in 1964 to 65. So this is what we can do. So I hope this shows us it's difficult. Yes? Then let's look at further progress. So we go to degree 3, single variable, then we're going to go higher. Then Garoha says, forget it, we cannot do it. We cannot find a symbolic solution for this. Okay, this is the end of the story. However, Newton tells that if you have a continuous system, which means if you're working on real variables, we still can do it very well. How about finite field for single variables? In the case of a single variable over finite fields, we have the Bullerkamp algorithm, which is pretty good in terms of solving the system, but the condition is that the degree must be low. High degree, we cannot do it. Okay? How about multivariate case? Multivariate case, even numerically is very difficult, and the final case is even harder. So that's why we could propose schemes based on the hardness of solving polynomial equations. So this is the mathematical idea behind. Okay? And then if you look at what we have done by now, most systems are constructed in the way such that all the public keys are quadratic polynomials. So which means the gi, x1 to xn are quadratic polynomials in terms of x1 to xn. Why is that? Okay, it's very important. Number one is we don't really think that going high degree is a good idea because any equation, any nonlinear equation can be reduced to quadratic equation by increasing number of variables. For example, the simplest case is, for example, I have given a set of equations x1 times to x3 equal to 5. By introducing a new variable y, for example, y equal to x1 times x2, then you can modify the equation into a 2 quadratic equation instead of 1 degree 3 equation. Therefore, in principle, we know, or we believe quadratic is the most hard to solve. If you can solve a quadratic, you can solve all others. Okay? And then I liked very much the comment that Diffie, this is a comment I think in Paris in 2000. So he said something very interesting. He said that if you look at the history of the so ISA is based on number theory. This is something we did in the 18th century. And ECC was done is based on elliptic curve. This is what we did in 19th century. And what is the theoretical, mathematical foundation for the multivariate scheme? This is the algebraic geometry. It's about how to solve system equations over finite fields. So this is what we have. Okay? And let's, again, talk a little bit about history. This idea of doing a multivariate was done very early, in 1980s. And early 1980s, the people trying. And the names here, just to give a few. Diffie, Feld, Tzu, Massimo, all others. They did many tries, okay? But they were not successful. More or less anything invented, it was defeated pretty quickly, okay? Yeah? But however, in the 1990s, things become different. This is, I think, I attribute most of the work actually to Pataran's work. Okay, I think this is the major thing. So now let me start with the signature scheme. Okay, so this is something I hope after I explain to you, you can go home immediately implement it. Okay, this is as simple as that. Okay, this is called Oyevnik scheme. Okay, so let's try that. Okay. Before I go on, let me briefly talk about the signature schemes again. So again, the public key, the private key is computed inverse. Okay, signing is computed the inverse of the value, and the verification is about to compute the value. So that is it. And then there's a toy example like this. Give document 201, and you have a signature. You can compute it, and to verify, the point is about to compute the value of the polynomial, and you know if it's true or not. Okay. And to sign the document, again, is to solve a system of equations, essentially. But if we know how to efficiently compute the inverse, then this is done very efficiently. Okay, so this is it. Okay, let me now introduce the scheme. Okay, this is the first scheme designed by Kimlis, Pataran, and Gomai in 1999. So that means what? 17 years ago, yeah, almost 17 years ago. Okay, so the idea is very simple. Okay, so the idea is that the public key part. F, often we call the central map. And this is a composition of F with a linear map L, invertible linear map L. Okay, so this is a composition of two maps. Okay, and the key construction is the idea of pattern one of being what is called oil vinegar system. Okay, so how do I construct map F? The F consists of F1 to Fo. So we have two variables here. One is called O. This is the O number. This is the oil number, and then another number called V. This is the vinegar number. Okay. So therefore, the number of variables is O plus V. Yeah, and the number of polynomials is O. Yeah, so this is design. And what the polynomial look like? Now the polynomial looks like this. Okay, the polynomial looks like summation of xi xj prime. So the primes are the vinegar variables, and then xi prime xj prime, and then plus the linear terms. So we don't care so much about the linear terms. So let's look at the quadratic part. Why do we call it oil vinegar polynomial? Maybe someone can tell me, why? Why do we call it? What is missing, maybe? Yeah, do you have oil with vinegar, vinegar with vinegar, so therefore what? There's no what? There's no oil with oil, right? So that's the idea. Yeah, this is a quadratic form. The quadratic form, you have pairing of oil with vinegar, vinegar with vinegar, but there's no pairing with oil and oil. So you miss some quadratic terms. So that's the basic idea. I think these French people are like Chinese. We love food very much, so we like to use food to name things. So here, if you look at it, the idea is what? Oil, vinegar, you never mix them completely. So this is the basic idea. Okay? So let me repeat, right? So this a central map F polynomials, and each of them is what is called the oil vinegar polynomial. That means inside the polynomial, you do not have quadratic term consist of oil and oil. So that's the basic idea, yeah? And from what we talked before is the verification part is very easy. We just compute the value of the quadratic polynomial. The point is how to invert the map, that's all. Okay? And if you look at a little bit, the systems, you can see we parts, yeah? Okay? So in a pre-image of the map F, what you do is you randomly to the vinegar variables. Okay, that's it. You just assign it. Let's see what happens. Yeah. So if you assign value to vinegar variables, what? Xi prime, xj prime disappear. It becomes a constant term, and here become linear term. You only have what? Linear terms of xi, all you go variable. Then you solve the linear system, and that's it. You find the pre-image. That's how you invert the map. This is a genius idea of Patron, okay? Yeah. So what he did essentially is converting what is called a linearization attack into a system design signature schemes. Okay, he converted attack method into a design method. This is what he did. Okay, is it clear how to come invert, right? You just assign the value. Of course, this system become a random set of linear equation. It's possible your system have no solution. What do? If you have no solution, you try to assign another value randomly. And because the system is random, we know there's high probability you will find the pre-image. Okay, so that's it. So that's the basic design. Okay, so this map F is easy to invert. Here, I would like to emphasize very much, this invert is not in the strict mathematical sense the inversion of a map, because this map is not bijective. This map is from, if the finite field is called K, is from K to the O to what? This map is K to the O plus V to K to the O. So you have a large space, you crunch into what? Into a small space. Okay, this is a surjective map. Therefore, it allows you to what? To invert. So there are many pre-images, which means there are many valid signatures. Of course, we only need one. That's all we care about. Okay, so this is it. This is the basic design. Okay, so let's go back quickly. If you look at this, why do you need the L? Because F is in the oil vinegar shape, right? If you look at it, you can see there are certain terms disappearing, right? So what do you do with the L here? The purpose of L is to mix them up because you do a change of basis. Afterwards, if you do a change of basis, you cannot separate the L oil vinegar anymore. That's the basic idea. Yeah. So this L serves the purpose of mixing everything. It's like you're making a salad, right? You just you shake it or you mix it. Okay. So that's it. So that's the basic design of the system. Okay. And initially, actually, Patron designed what is called a balanced oil vinegar, which means O and V are equal, and we can defeat that easily by this is done by keeping this as Shamir. Okay. So the design will require the two cases are bad, which is equal. V is much bigger. If it's much bigger, also not a good idea. So what do we like? So in terms of selecting parameters, we like the case where essentially V and the O, the ratio is about 1.5 to 3, something like that. Okay? Of course, it depends on what the security requirement is. So that's what we like to have. Let me emphasize again, V should not be too large. Okay? This is also easy to be defeated. Okay, so this is a basic state of art now. Okay, then you would ask, how about solving those guys using polynomial solving algorithms? Okay, I will not talk too much about it since we will say something about it. But the one thing is that if you do experiment, you can see this is very difficult to solve it. Those systems behave just like a random system. Okay, so this is what we know now. Okay, yeah. Now, in addition to direct attack, of course, you can also say, can I find something which can convert back into the oil vinegar space shape? Yeah, which means I want something which can help me to invert it. It turns out the best way to do that is again what? Is again becoming a problem solved quadratic equations, which means the problem to find the equivalent keys is again can be converted into solving polynomial equations, quadratic polynomial. So essentially same type of problem. This is what we can do. Okay? Yeah, so this is the state of us. Okay, and if you look at this oil vinegar scheme, there's one thing you don't like very much. Your signature, the length of your signature is O plus V, and V is bigger than O. So which means your signature is at least twice as long as, maybe 3 times, as long as the document. You would like to see, is there any way we can improve the system a little bit, make it a little bit more efficient? So this is some work done of me with my colleague Dieter Schmidt. We propose to do something which is a stacked oil vinegar construction, and we call it rainbow. Okay, the goal is to make system more compact. That's the goal. Okay, and the basic construction is very similar, except we also add one more nonlinear map in the front. Okay, and called to mix things up and the polynomials. Okay, so this is what we do, and I just tell you the construction. Okay, this is very simple. So in the oil vinegar, have oil vinegar. That's it. You're done. So here we have 2 layers. Okay, this is just one example. So what you do is first you define map F1. So what is F1? F1 is an oil vinegar scheme where the size of oil 12. Sorry. Here it's 12. Okay, and then the number of vinegar is what? 18. So you have 1 layer of oil vinegar. Okay, and then in addition you do one more, which means you will use all the previous construction, which means I use X1 to X30, all of them, and then I add 12 more oil variables. So in the end, you have 24 points. Okay, you stack them together. 2 layers. Okay, so this is the basic construction. Okay, we call rainbow 18, 12, 12, which means in the first layer, the vinegar is 18, and in the second layer, the vinegar is 30, and then the okay, the goal is to make it more efficient. Okay, make the key more compact. Okay, so this is and if you look at this, okay, a scheme, okay, this has very nice compact properties. Okay, so in this case, what I suggest, so if you choose the right size finite field, then the signature is essentially 400 bits. Okay, so you can do that. Okay, so if you do this, okay, and then in terms of computation, you know from what I told you earlier, the only thing you have to do is to solve linear systems. Therefore, it's highly efficient. Okay, in the case of rainbow 18, 12, 12, essentially encryption means you solve 2 sets of linear equations, each with 12 variables, 12 equations. Okay, so there are work done on implementing this. Won't talk too much about it. What I want to tell you is that these are very highly efficient because you only have to solve simple linear systems. And also we claim that the people who did the implementing claim has nice natural properties to resist side channel attacks. Okay. Of course, people are doing further optimization, and for example, Professor Yang and Chen in Taiwan are doing further implementation on this. So I will just stop here to talk about the design itself. Okay, then let's look at security just slightly. Okay, so in terms of the security, the first design the oil. So we designed it in 1999. By now, we didn't make much progress in it. In the case of random, the security changed slightly. Okay. In attacking random system, one of the goals is to separate them, which means if I can separate F1 from F2, you can defeat it much easier. So it turns out to separate them, we can call mean rank problem to solve it. So what is mean? Mean rank is very simple. Mean rank problem is you have such set of matrices. What you want to do is do linear combination of those matrices to achieve minimum rank, not 0, of course. Okay, that's it. That's a mean rank problem. So in addition to algebraic attack, the rainbow system has a possibility if you can solve mean rank problem efficiently, and what? You can defeat it. So in terms of mean rank problem, So in terms of mean rank problem, it turns out it is still a very hard problem. So what we know is theoretically, if you have m polynomials, if you have m non-invertible matrices, then to reduce rank by 1 is again the NP complete problem. So this is a very good. So overall, I think mean rank is also a very difficult problem. Maybe Ludwig will talk a little bit about it. Anyway, I don't know. But again, solving mean rank problem, the main technique is again to solve polynomial systems. To reduce the to reduce rank, you have to solve polynomial systems. Okay, so this is okay. So this is the first part. So I'm done with telling you about unbalanced oil vinegar and the rainbow system. It's very simple. Okay, any question, anything? Yes?
Where does the name rainbow come from?
Because it's just multi-layer, right? You have you have a rainbow, it's one layer on top of the other. So that's the basic idea. Yes?
You combine two layers?
Two layers, yes.
So we can extend multi-layer or we get three?
So that's the three. So from what we see, actually two is the best. Because once you do three, the mean rank problems start to become clear. So you have to balance two things, yeah? So here, I mean, three is doable, but yeah. So you have to consider mean rank problem. So right now, I think we believe two is the best. Yes, very good question, yeah. Okay, so this is it. This is what I mean, this system is what? I mean, I assign this implementation testing a rainbow system to my undergraduate students. There's no problem, right? Decryption means, I'm not sorry, signing means what? Solve a linear system, right? Evaluate, sign. Verification, evaluate polynomials, no problem. Very easy, very simple. Of course, security analysis is a little bit subtle. And maybe here I should emphasize again, I mean, I said it already, so how do you attack it? Number one, solving systems. You apply global basis and so on. This is a hard problem, we know. And number two, you do mean rank attack. Mean rank, again, to solve mean rank, the best known method we have now, again, is to solve a set of polynomial equations. Again, that's a hard problem. Okay, but here you have to be careful, because these are not exactly the same problems. Okay? Okay, so that's it. So this is the first. Okay? Yeah, so this next one I'm going to talk about is the HFEV minus construction. Okay, and maybe again, any questions, anything? Okay, okay, so let me then start with HFEV minus scheme. Okay? So HFEV minus scheme, HFE minus scheme. So HFE is a hidden field equation, stands for V is vinegar, so vinegar comes from oil vinegar. So we already talked a little bit about it. Here, from mathematical perspective, I call construction big field construction, which means, so this is related to what Matsui did, okay, which means we convert the problem building systems of a small finite linear space of finite fields into a single large field. So that's the basic idea. So let me start with talk a little bit about the history, how things done, okay? Let's look at the setting again. So we first choose a small finite field K, okay, suppose the size is Q, okay? Now, instead of looking at the dimensional n space, because we have n variables, what we do is we are looking at the degree n extension of the finite fields. Okay, so this is done by kx, quotient of gx. So gx is a degree n irreducible polynomial. Okay, and the key idea is very simple. Right? The key idea is what? As a vector space of a finite field, k bar, the degree n extension of the space can be viewed as an n-dimensional vector space of the small finite field K. So these two things mathematically identical. So you can have a map to map one to another one. Okay? And if you think a little bit from a mathematical perspective, what is elements in K bar? Elements in K bar are polynomials of a degree up to n minus 1. So if you pick out every single coefficient, you get a vector of a size n. So therefore, you can identify these two. Okay? So the idea of the bigger field is very natural. So if I cannot do well over the vector space, instead I will do something over the large space, a large finite field, then I just use the identification, moving the map to what? To the vector space. Okay, so this is it. This is the basic idea. Okay? And this idea was proposed in 1988 by Massimo and Imai. Okay? Maybe, I don't know. This is actually, I saw this book even earlier. It was published even earlier in Japan, is that right? Which year is it? 85, okay. So Japan, they do something different. They always publish the result in Japanese first, and then they publish it again. So this is done by Matsumoto Imai, okay? Okay? So this is slightly different, but essentially the same, okay? So remember what I just did about the rainbow. We have two L1, L2 on the end. So these are two linear maps on the end. But in the middle, instead of writing F, in the rest, I write the F composed by phi and the phi inverse. The reason is very simple, because we do construction over the large field, and I need the phi and the phi inverse to move the map down to the vector space of finite field. So that's the base idea. Okay, so this is the construction. Okay, and in the case of a Matsumoto, so this is a if you draw the pictures, right? So constructing a finite field, vector space of finite field, you build what over top, over the large field, then you phi and the phi inverse pull it down. Of course, you can also move it back up. And in terms of attack, this is something I will mention a little bit later. Okay, and the first idea was used by Matsumoto Imai to Matsumoto Imai crypto system. F is very simple. It has only a single term, which is x to the q to the theta minus 1. Q is the size of a finite field. Okay, this is the construction. Yeah, it's very simple. Okay, yeah, and then you do all the things I just said. This one you can convert into a quadratic equation and so on. Okay, so the inverse is very easy because we choose q to the theta plus 1 with co-prime with respect q to the n minus 1. This is very much like RSA, right? So therefore, the map is invertible. You can easily convert the map. So this, I will not talk too much about it. Yeah? So this is the basic construction, okay? Yeah? And the toy example I gave you earlier, I used Matsumoto Imai construction to show you how things was done. Those are toy examples, yeah? However, this scheme was defeated in Patran in 1995, what is called a linearization equation method. Okay, and so I don't want to talk too much about linearization method. I just want to tell you linearization attack is essentially the same as the Euler-Linear construction. These two are identical. Okay, so what Patran essentially did, so Patran in 1995 invented linearization, and in 1999 he converted the idea of constructing to build a linearization equation into solving what? Into design of Euler-Linear. So this is a very nice construction. Okay, so this is it. Yeah, and then Patran said, this thing done by Matsumoto Imai, the specific selection of the polynomial may not be a good idea, but the idea itself is nice. Meaning what? We will do construction of a large field and then move it down to the small vector space of small finite fields. So he proposed, instead of using the single term polynomial f, he said, let's do a relatively low degree polynomial, which means my fx, which is the central map, are constructed by the following polynomials, okay? But the degree has to be controlled. Why do I need a control degree? I already mentioned a little bit earlier about Bullet-Campbell algorithm, right? Because to invert the map, in this case, you have to solve a single variable polynomial equation of a finite fields, and you need to use the Bullet-Campbell Mason algorithm if it's over GF2. In this case, the degree cannot be too high, because the degree too high, I cannot solve it either. We cannot solve it either. Okay, so this is the idea. Okay? And Patran was very happy about it. I think this was also a very good idea, I think, and Patran was very confident in security, okay? However, that's not the case, okay? So now the global bases come in, right? So we try to solve, we can attack system using global bases, and then soon after, okay, Forget and Ju together, they broke the challenge 1 of Patran. Okay, this is a system with 80 variables. That's come as a very big shock. Okay, it turns out HFE is not that a good idea in the case if the degree D is low, because the compactness with controlled by degree of regularity, which I will explain a little bit later, is determined by log QD. So if D is small, algebraic attack is very efficient. If D is very large, it's very difficult to decrypt. So that's what happened. Yeah, so this is, in addition, there's also called a Kubernetes-Shamir mean rank attack. So if you look at the polynomials, itself, okay? So what the Patran Kubernetes-Shamir realized is that I can associate each fx with a quadratic form related to the coefficient aij. Because the degree is low, which means this quadratic form has a very low rank. So therefore, again, this mean rank attack method can be applied. So what they claim is if the rank, which means if the D is low, we can actually recover an equivalent secret key to solve this. Okay, so this is, okay. How about theoretically? So at that time, for example, in 2006, Grambolan, Ju, and Stan, they showed that if Q equal 2, in the case of a Q equal 2, to break the HFE system is a quasi-polynomial. Okay, it's not exactly mathematical proof, but they made a very reasonable argument. Okay, So from this, the conclusion is about HFE, sorry, not HFE. HFE is not a very good idea in the sense, if you want a secure system, you are very inefficient. Okay, that's the conclusion we can get. Okay, does it mean it's dead? No, it's quite contrary to that. Okay, in 2004, I did some work apply what is called internal perturbation. So I think I will not go over the details of this because it's a little bit troublesome. The fundamental idea actually is related to learning with error. Essentially, what I did is I add some noise to the system to improve the security and so on. Okay, so this F1 to Fn, the small one, are the noise. You add the system to try to improve security. But for such a perturbation construction, that you have to do a search of a size q to the r. R is the number of a so-called noise variable you will add to the system. Okay, and that's make the system highly inefficient. Okay, so that's the problem. Yeah. Nevertheless, we build those schemes and so on and so on. And for the turns out we find something even a little bit more interesting in the sense that if you have HFE system, if you do not use q equal to 2, which means if you do not use character 2, if you use all the characteristics, actually the algebraic attack is not so dangerous. Okay, which I explain a little bit later. Okay, but overall, use it to do encryption is not a good idea. Okay, however, again, Pateran and Gobain and etc. They say, okay, maybe it's not a so good idea to do encryption. Let's try to improve it to make it into something for signature. Okay, this is what they did. Okay, the idea is very simple. What they said is that, okay, I have HFE. I already explained to you earlier what is oil vinegar. So he said, let's just combine HFE with oil vinegar together. Okay, to make the system somehow more random. This is the idea. Okay, and then which is remove a set of polynomials. Okay, and the construction of the HFE V minus is you add a few vinegar variables to mix into the system. That's all. Yeah, so I'll give you the formula here. Maybe it is a little bit difficult to understand, but if you think a little bit about what I said earlier about the oil vinegar construction, the idea is essentially what? The same. Okay, so you have HFE system, and then you add some vinegar variable into it. Okay, and then the idea is that when you need to invert the map, you will guess the value of the vinegar variables, and it will move back to what? It move back to a HFE system. Yeah, so that's it. Of course, and then we have applied what is called a minus method. Minus method just remove a few polynomials. Okay, and this idea minus is first invented to prevent the so-called linearization attack, and that was used by Pateran design what is called S-flash. Okay, yeah, so that's it. So this is the basic construction idea. Yeah, so if you think a little bit about it, the mathematical idea is very simple. You have the oil vinegar idea, you have the HFE idea. You just put them together. You have an HFE system, you add a few vinegar variables, mix into the system, make it more random. And then you take away a few polynomials. Yeah, so that's it. That's the basic design. Okay, so this is a key generation process. Okay, I think I do not need to go over the details of how it's done. Essentially, it's, you just guess the variables of vinegar and you do other things. Okay, so I will not go over the details to do that. Of course, again, you not invert the map F solve the system linear equation, system of polynomial equations use the Berlekamp algorithm. Therefore, the degree D cannot be too high. If it's high, it's highly inefficient. Yeah. So this is what? This is the basic idea of HFE V minus. So again, so this is not a Gobain. I made a mistake there. It is Courtois and the Pateran in 2002. They proposed this HFE V minus scheme. Okay, you choose a finite field of and n, which is the degree of extension of the finite field, is 103. Okay, here the interesting is degree of the HFE polynomial. Here it chooses degree D to be 129. I mean, I think we all know what it means, right? 129 means what? 2 to the 8, 2 to the 7th plus 1. Yeah. Okay. To remember, the degree of the polynomial is q to the I plus q to the j, right? So here, maximum you allowed is 129. Yeah. So this is how you constructed the polynomial. So this actually part you move vinegar variables with what? With the HFE variables. Yeah, if you substitute by values, it becomes an HFE system. Okay. In the end, of course, you have to do A equals 3. What does A mean? A means after you build the system, you remove a few polynomials, which means after this, you take 3 polynomials out. Okay. So in the end, they have a F107 to 100. So which means at the end, the system you build is a system with 100 and only 100 what? Polynomials. Yeah? So this is a map shrinking the size, right? So therefore we can ensure is what? It's a surjective map. Therefore we can invert it. Invert which means find the element. Okay? And this is the quartz design. Okay? Think about this. This number 107 is essentially the size of signature. So it's very short. 107 bits. Yeah, it's very, okay. So this is very nice design in principle. Yeah. So this is the. So if you think about, if you ask me how about the security, the security system is related to mean rank. It turns out that the mean rank attached to the system relate to R plus A plus V. A is the minus term, V is the vinegar. This R is the rank original HFE polynomial. Basically log with the base QD. Okay, in the case of the, sorry, what did I do? Oh, sorry. In the case of this design, if D R is 8, the rank associated to the HFE polynomial is actually 8. Okay, and so if you think about this, for the case the rank they have is 3 plus, so the vinegar, sorry, I have to look at the vinegar is equal to 4. So the rank is 8 plus 3 plus 4. The rank, therefore the mean rank attack is essentially rank has to be 14. But because it has to be even, so 14. So you have to solve a mean rank problem of rank 14, and this is a very hard problem. Okay, and then you ask me, how about the algebraic attack? Okay, turns out there's some work done. So in 2007, we published a paper in Crypto and so on. We have actually fairly efficient way to fairly accurate the algebraic complexity, which relies on the concept of degree regularity. Sorry, I used it, but I'll explain. Numbers is Q minus 1. The Q is the size. So the Q is 2. 2 minus 1. R minus 1 if it's, R is use this problem system. So essentially, the degree regularity should be something like 14 minus 14 divided by 2 plus 2. So degree should be 9. So the degree regularity should be 9 for this system. Okay. And what does it mean? It means that to solve the system, you must deal with polynomial of degree at least 9 with 107 variables. Those are huge polynomials. Why it's difficult. Okay. If you look at this system, after its invention, there's no breaks, there's nothing we know new, more or less, after the design. Okay, we all somehow think this is very good. Okay, but there's one shortcoming of this system. It's efficiency. And at the very beginning, I mean, the signature takes about 10 minutes. So right now, we can do 10 milliseconds. At the beginning, when the system come out, when people implement it, we can up to take 1 minute to sign the document. 1 minute. But now we can do about 10 milliseconds. Okay, still is relatively slow. But why is that? Because in the case of signing the document, you need to solve a system equation with one variable, but the degree is 129. Okay, and there's the theoretical estimate plus n times d squared. But you should remember, these operations are over finite field size 1/7, which means I do this number of multiplications over, and those are pretty different in principle. So this is the fundamental reason why what? Why it's inefficient. Okay, so it's a good system, and I believe it's efficient. Okay, yeah. So this is. The system does not always have solutions. So you fail sometime, of course. If you fail, it's okay because you have so-called vinegar variables. You can try different values. Okay. So overall, I think the system is very good, but the efficiency is we have a problem. Yeah. So then one next question is make it better. Okay. This is very nice. Can we make it better? But if you go back to what I just mentioned earlier, okay, and if you look at give you an idea, isn't it? You realize the complexity, the attack complexity relies on this number, r plus a plus v. Okay? If you have, I don't really care about the a number. I don't really care about v number. Because a, just add the polynomial back. V is a vinegar variable. You're just guessing it. Okay? If I care about what? Inversion of the three, if I know r makes what? R makes the inversion very difficult. Why don't I do something different? Meaning what? Let me reduce r, increase a and v. That's the basic idea of what we did. Okay, so this is a paper published in HCrypt 2015. We said, let's think a little bit about it. Okay, so here I would like to emphasize at the time when Patarani designed the system, we actually do not know so much about degree. We don't know anything of this. Those people, I don't know how they did that. They never explained to me. I think they just had a hunch. They just said, let's do this. Okay, they choose d equal to what? 129. So with what we know now, we realize, no, maybe this is not a good idea. Let's what? Let's reduce the degree d, which is make the r smaller, but increase a and the v, because a and the v does not give me additional computation cost. Okay? So why don't we do that? Okay? And so that's exactly what we did. Okay? So we did think about it, say, okay, let's again start with what Patarani has done. Yep, those people have done. We can choose D. So what's possible with D? D could be what? D has to be q to the I plus q to the j. Suppose q equal to 2. I and j can be 0. Or for the first, you can D equal to 2. This turns out to be a very bad idea. Okay? There are many things related to that. Okay? And then let's say degree 3. 3 is 2 plus 1. And this is a bad, because degree 3 is essentially a Massimo Imai system. Okay? So afterwards, 4 is bad, of course. And the next one is 5 and 7. Okay? Yeah? But for 5 and 7, if you look at the mean rank attack, the R is actually exactly equal to 2. Okay, this is related. This rank is the same rank as Massimo Imai, so we're not so confident about that. So instead, we suggest choose q equal to 9 or 17. What is 9? 9 is 2 to the third plus 1. 17 is what? Is 2 to the 4. 9 is 2 to the third plus 1. And the 17 is 2 to the fourth plus 1. Okay, this is just it. Yeah? So again, let me emphasize, right? The goal is to make the system more efficient without sacrificing any security. So we look at the choice of degree 1 by 1, we realize maybe we should try 7 minus 17. So this is what we did. Okay? So we look at those systems, and then you say, okay, so you have this theoretical estimate of, and it is really true. So if you don't believe me, let's just test it. So we did experimental work to look at the degree regularity. And with V and so on. And if you look at them, they look very good in the sense of what? The degree regularity is more or less behave as we want. Okay? Yeah, the degree regularity is going up, reach to what we estimate. If the n is too small, of course, it should not reach the level, but when the n is big enough, it reaches exactly what we estimate. So this is the point. Okay? And for D17, this is essentially the same story. What it tells us is that if you do this kind of attack, algebraic attack at least, if you reduce D, make the degree lower, and increase A and V, the attack indeed goes up as you predicted. It doesn't affect the security. So that's it. So then we say, okay, this looks good. So then let's try to what? Try to do that. Yeah? So our selection is very simple. For example, which one of the case we choose so-called D955. Okay? And 1744. So what D95 means? D955 means with the HFE polynomial of the degree 9, the number of vinegar variable is 5, the number of minus variable is minus number is 5. So which means what? I will add 5 vinegar variable to the system. I take out 5 polynomials. for the case of 17, for d equals 17. So 17 is equal to 16 plus 1, which is 2 to the 4th plus 1. In this case, we suggest choose degree equals 17, and in this case, we only need the a and the b to be 4. Because the rank of the HFE polynomial goes up by 2, therefore, if we the same security level, we can just actually has a few vinegar variables and minus numbers. Okay, so for doing this, and if you do estimate the degree of attack complexity, so what we have is that the security of algebraic attack should be at least 2 to. So this is what I meant. So this is our proposal. Okay. So this work was done last year, and this Algebraic Attack. So this is H-encrypt. So in the end, we proposed the following parameter. Okay. So this is the case where first, so we have 95, 95, 94, 17, 44, and 127, 946. So what does those numbers mean? So let's just look. 127 means the number of variables is 127. 9, which means the degree of the polynomial HFE is 9. And the 4, which is this case, is the vinegar. So I have 4 vinegar variables. Oh, sorry, 4 is, this is A. The minus numbers, which means we remove 4 polynomials. 6 is the number of vinegar variables, which means we add a 6 vinegar variable to the system. Okay? And the last one, we expect the security level to be 123 bits. So this is the basic, the idea. Okay? And of course, in the original scheme to put by a birthday attack, they have to invert the map a few times, and this is a new paradigm to do this signature thing, which I will not go to details about it. And just let's look at it, the parameters and the key sizes. Yeah, so to compare with them, and you realize there's one disadvantage of the multivariate scheme is we have a relatively large public key size. Okay, so the key size, sorry. Yeah, but in terms of efficiency, okay, originally course before than the system before, but if you look at the new things we have done, they are comparable in terms of computation efficiency. Yeah, especially degree 95 and so on. Yeah, if you look at the signing time, if you compare the signing time with doing better. Yeah, so this is what we did. Okay, but here the point really I would like to emphasize is the reason because we start to understand, or we understand now, the applied complexity in the theoretical foundation of the degree of regularity. Okay, that's we dare to do this. Okay, I don't want to say that the original design is bad. The original design was done is actually they had a good hunch, but we didn't have the information on how to estimate complexity accurately at that time. But now we do. So why don't we use it? Okay, so this is so we give a different name called the Gui. The Gui is just because all the Chinese pottery has 3 legs. I mean, because it's HFE, A, and the V. So say the first leg is HFE with vinegar and minus, and something like this, slightly shorter. That's all. Okay. Front leg is HFE, the back 2 legs are minus vinegar. This is just for fun to call it. Okay. So what we can take away from this is that we realize for the HFE V minus system, you can reduce the degree without sacrificing any security. And by doing that, we can achieve efficiency as comparable with RSA and the ECDSA. Okay, so that's it. Yeah, that's the key point coming from this second part of the lecture. Okay, so then I'll stop here. Any question, anything? Yes?
I don't see why it should be secure against attacks by quantum machines.
Oh, the quantum machine.
Polynomials over finite fields,
Yeah.
won't they be cyclic?
Sorry, I didn't understand your question again. So you have a polynomial system equations, right? Mm-hmm. As far as I know, of course, you can use a global algorithm to make it more efficient into the brute force attack. Otherwise, we don't know a quantum computer can do anything better. Yeah, because it's an NP computer problem. I don't think quantum computer can do that yet. Yeah, so that's the idea. Of course, but those are not random maps, right? You always have mean rank to worry about and so on. But again, if you want to solve mean rank problem, again, solve polynomial system. So by now, as far as I know, we don't have any better algorithm in terms of using quantum computer to do solving polynomial systems. So therefore, yeah, okay, good, thanks. Okay, any other question? Yes, please. Which one? This signing time? I'm sorry, I didn't understand your question. Okay. No, okay, let me translate his question then. Okay. So he was asking about the complexity estimate. For example, the complex estimate here. There's a complex estimate here. Yes. Okay. In terms of the estimate of the complexity of performing global basis. Okay. So of course, I said a little we could talk about it, but I will give a very quick. So global basis in the end, so let me put it this way. Even though we humans can claim we can solve nonlinear system equations, but we are not so smart. What we do in the end is always convert solving nonlinear system into system linear equations. Okay? So in the end, if you do algebraic attack, in the end, you have to solve a huge linear systems. Those estimates coming from estimate of the complexity solved as linear system of a certain size. That's it. That's where the number comes from. It's not experimental, it's a theoretical estimate. Yeah. I see what I mean. So these are theoretical operation estimates. Yeah, not the bits operation estimate. No. Yeah. Oh, that should be very easy, right? This is basically we're counting number of multiplications, yes, over the finite fields. If you can convert the number, each multiplication, how many bits operation you have, then you can have a pretty good estimate. Yeah. Yes. So these are number of operations over the finite field we are working on. Yeah. So it yes. Okay. Yes.
Attack is based on only theoretical. So
yes.
any others such as side channel attack?
Oh, side channel, of course. So I don't know. First, I don't know much about this. Okay, but there are people tried it. So in terms of if you look at the system, right, you have the secret keys, right? Of course, in principle, you can always read out the secret keys one by one, but the size are pretty big. They're spread all over the place. It's very difficult to do, as far as I know.
No research?
There's some people did something, but no publishing. So I asked some of my friends are expert in this. So I asked them, they do something. They said they cannot do anything. This is all I know. Yeah. So I'm not an expert in this, so I know. But we do not. It's like ISA, right? ISA, you have this multiplication of, so you have a square or multiply two numbers, therefore you can read out the secret. We do not have anything like that. So essentially means you have to read every single bit of the keys in order to do that, which should not be easy as far as I know. Yes?
I think that for the complexity of the global basis,
Uh-huh.
and the idea is very important.
Yes.
So it seems you assume that some radicalness of the idea.
One more time. What?
Radicalness.
Very good. Okay, this is okay. So, very good. So you are a mathematician, so I'm a mathematician. So, okay. So the system is a system, particularly in this case, is a system where there's only one solution.
Yeah. Also for the complex analysis, it looks like some operation, number of operations of the Macaulay matrix.
Yes, exactly. Yes, because so I think Ludwig explained to you. So if you do global basis algorithm, as I said, we are humans. We are not so smart. We can only solve linear equations. There's nothing else we can do. So in the end, you convert solving the system, solving the nonlinear system into a system of linear equations. And this estimate coming from how large the linear system is.
Other question.
Uh-huh.
You use some and the polynomial basis of the expression of the finite extension. Of the
Yes. Mm-hmm.
But are there some use of the normal basis?
One more time. I don't understand. A normal basis, yes, but the normal basis idea is essentially global basis, no? It's essentially the same thing. Yes?
It gets the computation more efficient.
Yes, in principle, yes. But if you do it practically, I'm not sure. Because this, if you remember, we always do, you remember this have L1, L2. We do a random change basis. So we suppose originally you have some hidden structure, but those are all gone. You do not know yet. So therefore, when you do a linear algebra, you cannot estimate this size will be 0. This, we cannot do that. So therefore, it's very difficult to do it. Yeah, thanks. Yes. Okay? Okay, any other question? Yes. Yes.
And your other attack, I assume you're using last computers for that?
Yes.
I was wondering, have you tried or imagined theoretically how it would work with quantum computers, and if so, if there's any improvement?
Very good question. Very good question. Yes, this is something we have to deal with. I mean, I tried myself. I couldn't say anything more intelligent than what is known now. Therefore, I didn't write anything. So what I want to say is that mean rank attack, the best mean rank as far as I know, in the end, again, becomes a problem solving polynomial equations. Okay, they all reduce to how complex is to solve a system of polynomial equations. Okay, by now, I haven't found anything or asking around. We don't know anything that we can use quantum computer to help us make things better. Oh, except, of course, you can always, of course, for the signature scheme here, we're a little bit ambitious in the sense, our signature is very short, 95 bits. And if you do global algorithm, of course, you claim whatever. This is, we haven't to take a full consideration of that. But we can increase n, there's no problem. Yeah, but as far as I know, I do not know any work that tell us that you can use a quantum computer to make solving polynomial system much better. As far as I know, no, I don't know anything like that. Yes, very good question. Yeah. Okay. Okay. Any other question?
I want to know if your signature size is very short.
Yes.
I want to know how you decide several times to prevent
At person attack, yes. Maybe here I don't want to talk about it. I can explain to you later. It's a little bit technical how it's done. Yes. So, but what I want to say is we didn't do anything new. We essentially emulate what Pataran and have done. Okay, they did the same thing. We make it a little bit more efficient. That's all. Okay. Yes. Okay. Any other question? Okay. So if not, let me go to the last part of my lecture. I mean, I hope I will not drag on forever to prevent you from going for lunch. Okay. So this is done. And then, now let me talk about encryption. Already, you probably can see it already. I think doing signature is pretty easy for us, for multivariate. We had a lot of problems, yeah? We have something done based on the same line, for example, PMI plus, HFE plus, and so on. They are highly inefficient compared to the signature schemes. So for years, I have been trying to make it better. And it is hard work. And I mean, maybe 2 or 3 years ago, I come up with my students' idea called the simple matrix scheme for encryption. So this is very new. I think it's good, but of course, I have to wait and see what it says, right? So let me just explain. The goal of this lecture, again, is to explain the basic idea. So like everything I do, I like something simple, okay? Everything I do here is simple, nothing more complicated. So this construction is also, again, very simple. Okay? I mean, again, this can be an undergrad project. Should be no problem, okay? But before I would like to say a few words in terms of the shift in the paradigm. If you look at the HFE, model dynamic, and so on, we have been trying to build systems is from n to n, which means we are building map from k to the n to k to the n. And if you want to build an encryption scheme, I think it's a very bad idea. Why? Because if you have map from k to the n to the k to n, if you want to have decryption which be invertible, this map essentially bijective, then we have this differential attack. I mean, which I will not talk about because in the last PQC, I think Daniel is here, he gave a full lecture about differential, so I will not talk about this. If you look at the differential, you realize it's very easy to tell the difference between an invertible map and a random quadratic polynomial system. So therefore, maybe 5 years ago or so, and I realized, no, it's not a good idea to build a map from Kn to the Kn. I need to make the system, make a map larger. Meaning I need a map from k to n to k to 2n maybe. One of the fundamental reason I was thinking about is exactly because that. It's because if I want to k to the n, theoretically, it should not be possible if you want to have the property indistinguishable from random system. So after that moment, I had a shift in the paradigm, which means I want to build a system from Kn to the k to 2n instead of Kn to Kn. And that changes things completely. Okay? But one more thing I would like to emphasize here again. If you look at all the attacks that can break the existing encryption schemes, the most damaging property is mean rank. If you look at the HFE system, you realize this degree D is very important. The D is the rank, related to the rank. Rank low, algebraic attack works. Rank high, we cannot decrypt. So from all the work I've done by now, what I realized is that I'm not so concerned about algebraic attack. The reason is because once we understand degree, if we can use all the characteristics, we actually can do pretty well to prevent algebraic attack. What I really truly worry about is mean rank attack. So what I want to do at the time is to build something that has a high rank, properly related. Okay, so this is what I do. Yeah. So in this case, so I propose to build a scheme called this ABC scheme, which is based on matrix multiplications. Okay, so let me explain in the detail how it's done. Okay, so this is something very simple. Again, let me repeat. You should be able to understand completely. If there's anything unclear, you should interrupt me to explain. Okay. So what we'll do is we build a map from k to the n to k to the m. Okay, so n here has to be a square because we're using square matrix, and the m is 2n, which means this is a map from n variables what to 2n variables. So which means this is a system with 2n equations, n variables. Okay, and again, the key thing is the central map. Yeah, so let's go to, by now I think I can skip the details of this, and what I want to explain to you is how to construct the map. The central map should be km. Okay, so let me try to do that without sticking too much to what I wrote. Okay, so n is equal to s squared. What does it mean? Start 1 to x squared, so I have n variables. So I build the first matrix called A. So A is just x1 to xs, x2s, all the way, and just a matrix. That's it. And then the second matrix is B. What is B? Each entry of B are random linear combinations of x1 to xs squared. That's all. And what is C? C, again, they are random linear combinations of x1 to xs squared. I just built the three matrices, A, B, and C. Is it clear? Yeah? I built the three matrices. Yeah? And then what I do is I compute A times B and A times C. Since A and B both are linear functions of x1 to xs squared, if you multiply them together, what you get are quadratic polynomials of x1 to xs squared. Okay? So by doing that, I get E1, E2. So if you look at the entries of E1, E2, each of them are quadratic polynomials of x1 to x squared, and then I just take them up, line them up, then I get 2m, which is 2s squared polynomials. And this is my central map. This is the map F. Remember, the construction is always F and composed by L1, L2. Okay, the main constant is F. So that's it. That's the construction. That's it. Is anything unclear how it's done? Yeah? So I need to build what? I need to build a system polynomials. Okay, so here it's very simple. I design A, I do B and C, and I multiply A by B. These are square matrices, right? A times B, and then what? A times C. That's it. Okay. Then I take every entry out and line them up. They give me 2n. Sorry. X. It's as simple as that. Okay. Yeah. And then of course you compose L1, L2, which is not important yet. So, and then to decrypt, I have to apply the inverse of each of them. So of the key to invert F inverse. So let's see how we do it, right? So suppose I want to invert the map F. So if you look again, the entries of F essentially is what? A times B, A times C. That's it, right? So which means I know the value of A times B, I know the value of A times C. I need to find the solution. That's all. And E1, E2 are known. Okay? Yeah? So let me just go directly to the number 3. Number 3 is a generic one. Okay? So to decrypt, so here we have one shortcoming which we require A has to be invertible. If A is not invertible, I cannot decrypt either. So there's a small catch here. So let's pretend that A is invertible. How do I solve the system equation? It's very simple. You multiply A inverse on both sides. But the A inverse are symbolic A inverse, which means you treat each entry of the inverse as a symbolic variable. You don't care about them. But if you multiply A inverse per side, you will get A inverse times A inverse equals C. Remember, B and C are in terms of x1 to xn. And if you treat A inverse as symbolic variables, and what you get here, what? You get here is our linear system of equations. Do you agree? Yeah, the key thing is treat A inverse, each entry, as a symbolic variable. Yeah, so therefore, in this case, the number of variables jump from n to 2n. From n to 2n. But each system, so this equation gives me n equations. In the end, I have 2n equations, 2n variables. Do you agree? Then I try to solve it. So how do I do that? I will do an elimination, Gaussian elimination, to eliminate those symbolic variables A1 to from A1 inverse. Then the left are linear system equations satisfy x1 to xn. Then I solve it. If I cannot solve it, I already can remove enough variables, then I plug into original quadratic system, solve it, and we're done. So that's it. Okay? So I'm essentially done with my lecture about this. That's it. That's very simple. Is it clear how it's done? I mean, I just want to know, how do you invert it? So here I have assumption what? I have assumption A has to be invertible. You ask me, A is not invertible? Sorry, I cannot do anything for the moment. Okay, I give up. I say I cannot decrypt. And that's it. That's the basic idea. Okay, maybe I should here pause for 30 seconds. If you have any questions, it's unclear how you do this. Yeah, that's it. That's how you invert it. Yeah, once you can invert, you can decrypt, then you're done. So what you have to do is solve this system linear equation. That's the most important part of computation. And that's it. Then you remove symbolically variable coming from A inverse. Yeah, and then you're done. That's how you invert the map. Okay. Okay, assume this is okay, right? Then you would ask, how about the failure of decryption? There's a failure of decryption, but as long as A is invertible, and if you assume A is random matrix, no, the failure probability is 1 over Q, so which means in this case you should make a Q a slightly large, and encryption to sending keys, deal. Then you just do it one more time, so it's okay. So that's it. That's the basic construction of the simple matrix scheme. Yeah, I just modify two matrix. But the key I would like to emphasize is this is not a map from Kn to Kn. This is a map from Kn to K to 2n. I have much more. I have the number of equations double the number of variables. Okay, so this is very different from what we did before. But on the other hand, this is also very natural. This is, if you think about our Gamow system, this is exactly what a Gamow system is like. Okay, and also the system is the same. Okay, let me give you some example. For example, choose 4, which means in this case I use matrix 8 by 8. Okay, use 8 by 8, and then do all those things. Of course, in this case, the key size is very big. It's about 2 megabytes. Okay, yeah. So this is what one of the proposals we have, but the computation efficiency is very, very, very good. But then security analysis, you say, oh, your intention at the very beginning is to prevent a mean rank attack. What happened to your rank? And if you think about the design itself, you realize this is A times B, for example. A times B, there are 8 entries here, and the B is row times column, each is 8. So you realize the mean rank coming from the system is actually rank 16. And this is very high. So the security is very good, I think, into the mean rank attack, as far as I know. Okay? How about algebraic attack? Algebraic attack actually goes also very well. The point is the degree regularity increases as so which means if you don't achieve something, you can increase the n a little bit, your security is good. Okay? So that's what we did. Yeah, so this is the design for the simple matrix construction. Okay? So by now I don't know any, other attacks and so on, but so in terms of what we know, they look pretty good. Okay? And again, in terms of efficiency, the decryption is very efficient because essentially just like we did it before. So therefore, the inverting process, which is decrypt, is very efficient in terms of the computation. Okay? Yeah? And then afterwards, we did some more work. One thing we did a rectangular construction, which means instead of choosing A, B, C to be square, we can do something rectangular. The goal is, again, to eliminate, to reduce the... and also, we did something very unusual, meaning we also proposed doing what is called a quadratic construction. In this case, we propose something very strange. We choose A to be a random quadratic polynomial. Okay? So I can explain to you quickly what happens in the degree 3 construction. Okay? So what we realize you treat variables. So why not choose each entry of A as random quadratic polynomials? Okay, in this case, we build a system of degree 3. Of course, the key size is very large, but I'm highly confident of the security of the system because the system itself has no polynomial structure coming from it except a matrix, because the entries of A itself are random quadratic polynomials. Okay, so this is what we did, and with also we did. This is work I've done with Professor Nietzsche, Petzold here, both audience here, and also we try to do some work, try to eliminate the decryption failures, and we just put a new paper in the web. But anyway, so I think this work is just at the very beginning, and I think it's very interesting because it's a simplicity. It's just so simple. Just multiply matrices, put them together. Okay, I like the construction very much. So that's it. That's all I intend to talk about, and simple matrix construction. Okay, again, any question, anything? Hope I can. Yes.
So in case of simple matrices, so if you hide the central map by two linear map, L1 and L2.
Yeah, afterwards you do L1 and L2. Yes.
In case L1 is identity map, then is it written in your scheme?
One is identity. One is not a good idea. Reason is you remember if you do A times B, right? Each polynomial has only rank 16. Yes. If you do not do L1, this rank will remain 16. So I can identify. No, I don't suggest you do that. The point. So even though each rank is 16, right? If you do L1, you mix them up. So therefore, everybody achieve the full rank. You know what I mean? Do you know what I mean? So that's the first purpose of L1. L1 is to mix the polynomials. Yeah, so you should do L1. No, it's a bad idea. I think we should do much better. You can see the rank already. Then you can do more. Yeah, very good question. Okay. Okay. Any other question? Okay. So if not, then good. I'm perfectly on time. Okay. So I mentioned many times. I think I was about it. Okay. So if from what I already talked about now, you know what you worry about in terms of security analysis in the direct attack. Number one is the direct algebraic attack. Okay, this is what you worry about. Of course, the mean rank attack. Okay, and then here, of course, I would like to mention one more time about differential analysis. Is the method to break the S-flash done by Stern, Dubois, and Shamir, etc. Yeah, but since Daniel is here. Yeah, Daniel Smith also gave a lecture before, so I don't want to talk too much about it. Okay, some very important work is done already on differential analysis to show that the new designs, for example, in the later show this new Gui sanction scheme does not have any differential analysis weakness. Yeah. So now let's come back to the direct algebraic attack. Yeah. It seems Ludwig will talk about this. Any detail do this. Okay. But I would like to accept a little bit of the concept of degree regularity. Okay. So what is the degree regularity? Yeah. So since I mentioned many times. Okay. Okay. So degree about X. Let's just look at something about the XL algorithm. Okay. So what is XL algorithm? I'm not talking about global basis. So XL algorithm is very simple, not a bad idea. So you have a quadratic systems. Then you multiply by one variable. You go to degree 3, then do it in linear algebra. Try to see if you're lucky, then you can find a linear system. If not, you go up one more. You go up one more. You go up one more. Because we are working on a finite field, because we know there's only one solution, therefore we know the ideal generated by those elements is the same as the ideal generated by x1 minus a1, x2 minus a2, x3 minus a3, and so on. As the ideal is identical, which means if you go degree high enough, you will be done. You will find your solution because the linear system is inside the ideal. So what is degree reality? Degree reality is the following things. If you go from degree 2 to degree 3 and degree so on, normally what happens, you just keep going up. You do an elimination, there's no degree 4, which means if you have the number of polynomials of high degree, after you do elimination, you stay high degree. Okay? What is degree reality? Degree reality is the first time a non-trivial cancellation of the top degree occurs, and you will produce a new polynomial of a lower degree. That's the intuitive definition of degree reality. Ignore what I wrote on that. Doesn't matter. Okay? So this is the definition of degree reality. Is it clear what I'm saying? Yeah? So you have a quadratic system. If you're lucky, in principle, you just try to do Gaussian elimination to eliminate quadratic terms. If you have a linear system, you're done, right? But normally, you do not have any cancellation in the end. You do eliminations, the number of quadratic polynomials stay the same. Okay, you're stuck here. What you do is, let me explain again, XR, you just multiply by one more variable, then you go to degree 3, then you try to do elimination again to see if you're lucky to get something which is linear. Okay, so the degree reality is the first degree at which something drops non-trivially. And one phenomenon we know, it occurs all the time, but we cannot prove is that the polynomial system normally happens, that's it. Once you have one drop, the system starts to drop very much if you keep doing it, and the system will be done. So therefore, the degree reality now more or less tells me how high the degree I have to go in order to solve my system. Okay, that's the definition. Okay, this name actually is not good. I would like to change them. This is basically the degree reality. I would call it a mutant degree because I define something. So once you drop the elements, you produce what I call mutant. Okay, so degree reality is the degree at which the first time you produce what is called a mutant. Okay, and the interesting phenomena which we cannot prove. Okay, this is the fundamental mathematical question, which is why we drop and then all of them we're done very quickly. Okay, at the worst, as far as I know, we go up one more degree, we're done. I haven't seen any example you have to go more than 2. Okay, so therefore, knowing the degree of regularity is very important. It tells us the complexity of solving polynomial system equations, and it's very difficult to get this number. Okay, so but one thing again, I would emphasize non-trivial, right? Because there are trivial constellations. Right? You have 2 polynomials, you can multiply pi by pj, pj by pi, they cancel it out. But this I do not count. Okay, so therefore you have the modular of what is called a syzygy. Yeah, so this is the definition of degree regularity. Okay? What the claim is? The claim is a global basis algorithm terminated shortly after this degree. But I don't know why, okay? You do experiments, it just happens all the time. Okay, in general, in particular for random systems. Okay? So this is what happens. Therefore, knowing the degree of regularity is very important for us. And what is very nice is that we do experiment. This happens all the time. Okay? Yep. And so this is it. And one more thing I would like to emphasize is the mutant. The mutant tells me what? Your system starts to degenerate, right? Normally, you're just going up, up, up. Suddenly what? You start to have a non-trivial constellation. You build something I call mutant because you have a non-degeneration occurs. And those guys can help you to solve the system very quickly. So this is one of the reasons it works. Okay, this is the implication of a degree of regularity. Yeah, and then for the case of, so I will skip all the technical details. For the case of with my colleague Hodges, we proved the formula claims the degree of regularity is less equal to this formula, basically the rank of the HFE polynomial times q minus 1 over 2 plus 2. We prove an upper bound for the degree of regularity for the HFE system. And this is the basis of what we did for HFEV minus. Okay? And if you look at q minus 1 here, that is very important. So which means if q equal to 2, q minus 1 equal to 1. And that's why Zhu and Forget's algorithm could defeat HFE over q equal to 2. So if you do HFE, if you increase q, it's very difficult to solve. So therefore, choosing other characteristics is not a bad idea. Okay? So this is what we prove what is called the upper bound. What we really care about is the lower bound. But if you do experiment, it's very interesting, and you'll reach this upper bound all the time once n is big enough. So which means this bound is pretty tight. Okay, and this is the basis of the design of HV minuses. Yep. So again, which I should emphasize, this are very nice work in the sense of matching the experimental result with the theoretical result. We don't have a gap there. So we have a theoretical estimate, we have an experimental. You can see this number matches very well. So we are highly confident in what is going on here in terms of complexity analysis and so on. This is a very big advantage for the multivariate schemes. Okay. So we have those formulas here. Okay, those are very good formulas. But for the general lower bound, we don't have any, except I recently proved a case for do HF formula d equal to 2. Actually, I can prove something, which is a precise bound, not a lower bound. It's precise. I can prove the degree is exactly equal to the number. Okay, and that's a very encouraging sign. Okay, again, so I will mention the mean rank many times. The mean rank problem, again, we have to solve the mean rank problem by solving a system polynomial equations. So here the degree is also highly involved. How you do it efficiently. Okay, so this is it. So the conclusion I have for this section is what? The conclusion I have for this section is that essentially what we have to worry about is the problem. I think it's what you have to worry about as far as I'm concerned. Okay, if you have an algebraic attack problem, change using other characteristics. It should help you solve the problem more or less. But mean rank problem is very difficult to emulate. Reason because we want to decrypt. Decrypt must have hidden structures, and it's very much related to mean rank property. Since we're dealing in quadratic forms, of course, rank is the most important property involved. Okay, so that's it. Okay, so let me make a quick summary of what I talked about today. Yeah, so I think that for the multivariate case, we have a very solid foundation in terms of both design and the security analysis. Okay, and we are very efficient. Okay, easy to implement, but one shortcoming is large key size. Of course, there are people already working on reduced key size. For example, Algebraic Attack did some very nice work on how to reduce key size and so on. And for quantum computer attacks, I mean, here one audience already asked about it, but we haven't done much. So I essentially do not know any advantage using quantum computing in solving polynomial systems. But in terms of design parameters, of course, you have to know what exactly you're talking about. But we haven't done any work on that. Okay? And in then, thank you very much. This is the end of my lecture. Okay, thank you.
Thank you very much. So we have space for
Yes.
question and comments. Is there any questions?
Yes.
There are a couple for the degree of regularity that you define in the first order.
Yeah. Yes.
So and the degree of regularity is something different.
Yes, I think there's a misunderstanding here. The name, we should not use that name. Because degree is there's some way else using something different. So what I meant here, the definition I have is the first non-trivial degree 4. Yes, that's the definition I intend to use. Which means the first degree at which there's a non-trivial syzygy occurs. Yeah, that's what I want to use. So therefore the name, I don't like the name. Yes. Yeah. Okay.
Okay, other questions?
Okay, that's it.
Maybe I ask.
Okay, sure. Yes.
How many size is the
Bigger disadvantage, yes.
So how can you reduce the key size?
So for example, Algebraic Attack here, he suggests using some circular on the public keys, and then so therefore you can reduce by like 50%, 60%, something like that. And in the case of, for example, in the case of the simple matrix scheme, the reason I choose a large Q to the large Q is because I want to deal with the problem of the decryption failure, but that can be dealt with quite efficiently. But in general, I think the idea is, and if you think about from LWE to RLWE, what essentially LWE uses random matrices, RLWE uses a circular matrix. So we would like to apply a similar idea. I think Pascal already started working on this. This probably can help us. Okay. Mm-hmm.
Question?
Yes.
So I have some skeptical feeling about the first degree assumption.
Uh-huh.
And usually, if we think about the complexity of the basis,
Yes.
we have to think about some homogenization of the ideal.
Yes.
And we find some regularity of the
Yes.
Hilbert-Poincare series.
Yes.
And But in your case, you are handling a special case of the ideal.
Yes.
So it might be. I think there is some possibility to have some more precise analysis on the context basis. But for the first degree assumption, and this is too much for my field, and I think that you are handling about some zero dimension radical, and the solution is only a unique solution.
Yes.
So this means that each variables are so-called some in generic position.
Yes.
And it has very special forms. And,
yes.
And I think that to give a precise analysis, think about the fact that the order of the variable and the order you use in the.
Okay, so this is a very good question. Okay, he discussed about the role of the variables. If you think about what we are doing, we always do a change of L1, L2. What L2 does is do a random change of basis. So therefore, from this process, there's no difference between those variables. No, you can try it. There's zero difference because we randomize them already. Of course, you can say then maybe I find some way to go back, but that's a part of secret key you cannot have. So therefore, I mean your idea is very good, but I don't think in this case it works because we randomize the variables. Yes, not assumption. Yes, we prove the lower bound, upper bound, and then we do experiment, and it occurs exactly like this. So from the pure algebraic perspective, you're looking at the syzygies, which means you homogenize it. We don't care about lower degree. For example, let's look at quadratic syzygy. We only look at degree 2 part. What we are looking for is the first non-trivial syzygy occurs. Because if you don't have if you have no trivial syzygy, you have no non-trivial syzygy, there's no cancellations. Therefore, there's nothing you can do. So therefore, we're highly confident of what we're doing. No, I agree with you. You emphasize very much the order of the system. Yes, x1 to xn, which order you use. But because we do a change of basis.
But what do you think about the first pole? Because the last pole might be much better.
That is, I agree. But the last 4 is much higher. Somewhere else, it's much higher. So what also maybe I describe the first 4. What is the last 4? As far as I understand, the last 4 is at which degree at which if you multiply all these monomials, you will get everything, boom, done. That's the last 4. But you see what we did, so because we have a mutant, we have a first 4, we go down. Now from here we climb up again. Yeah. So therefore we don't have reached there. That's where last 4 is not important to us.
But for my small experiment, in some cases.
Yes, but in some but for the can be obtained as a last. But do you randomize a variable? Do you randomize?
Yeah.
But we haven't seen this in our experiment. We don't see any of this. So for us, there's no difference between any variables.
Maybe your case is very special.
It's possible. I don't know. Yes. But I still do believe the first degree 4 is what we concern most, not the last 4.
Interested in some theoretical basis of the assumption.
Yes, I agree, but we don't know much. The reason is if you look at how system solve is what here. You first go up here, you fall, you go up, you fall, you go up, you go up, and then you're done. That's what happens. Okay, we don't go all the way up because it's too costly. Because the higher degree is too costly. We don't do that.
So your assumption is that after the first degree,
yes,
the basis can be terminated very quickly.
Yes, that's what happens when BT is the first reach here, fall, go up and down. A few times, done. So therefore, we care about first time the force.
But for general setting, it's very extraordinary.
No, if you try, you can see the random system. You do experiment, it behaves exactly like that. No. Zero dimension case. We only care about zero dimension case. Because we always can guess the number of variables. You can guess a few. You always become 0 dimension, remember?
But I cannot understand the mathematical background of the first degree.
No, as I said, the mathematical background is...
We can guess some behavior of the computation, but there must be some hidden mathematical properties if the first degree assumption holds.
Yes, but I said earlier, we don't know, but it happens. If you do recommend it, that's very good. Yes, I thought about it for a long time. I couldn't do anything about it.
For the general setting, we may generate some counterexample easily.
Yes, artificial counterexample is you can, yes, I can do that too, but not HFE system. Because, for example, if you look at HFE, variables are identical.
I think what you must argue is, so you are thinking about all very special cases, not
yes.
general case.
Yes. I'm not sure. I think maybe Ludwig will tell you later, but in what we care about, you can see it happen all the time. We don't have any natural, I do not have any natural counting examples.
Do you have some mathematical insight about the
I have some ideas about it. Maybe I should not talk about it here. It's a bit too much for this audience. Okay, thank you, thank you.
Yeah.
Yes. Yeah, yes, yes.
Thank you very much.
Okay, thank you, okay, thank you.